So now that we've learned to work with exponentials and logs, let's go ahead and look at some nice applications where we can use those types of models to answer real life questions. Now, in general, this is kind of our basic exponential growth or decay model. So for an exponential, you're going to have your variable, which is in this case is a t. Usually it's time. It could be an x. In this particular model, this exponent might also get multiplied by some constant. So this k would be a value that would be given. E we know is just a number, that 2.718. We're going to use our calculator to find it. And remember that y sub 0 is your initial amount. So sub 0 initial amount at time equals 0. Now, if k is greater than 0, so that means if it's positive, then that means we've got exponential growth going on. But if you have a negative exponent, so that k value would be less than 0, then this would be an exponential decay model. Now, you're going to either be giving that model or you're going to be given some information so that you can go solve for the missing parts of that model. Let's jump in and look at some problems. Okay, so let's look at this first one. So I deposited $500 in an account. It pays 6.75% interest. Compounded continuously, how long will it take to double the money? Okay, so since it's compounded continuously, you should be using your PERT formula, A equals PE to the RT. And the A is your ending amount. And since I'm trying to double my money, I know that I'm going to end up with $1,000. My P is my initial, which is 500. E to the 0.065, I'm sorry, 0.0675. T. And then I'm going to solve this for T. So the first thing you're going to want to do is divide by the 500. So that's just going to get you a 2. And then you have E to the 0.0675 T. And then you're going to go change that into a logarithm. So natural log of 2 equals 0.0675 T. So in my calculator, I'm going to just do a natural log of 2. And I'm going to divide it by 0.0675. And I have my T is equal to 10.27. And that would be measured in years there. Okay, so what if it's compounded monthly? Okay, now you're using your other formula. So we're kind of practicing all these formulas we've got. On that formula, the compounding monthly would be A equals P, and then in parentheses, 1 plus your interest rate divided by the number of times you compound it yearly. And then you take it to the N times T, which is really the total number of times it'll get compounded. So let's fill in our numbers here. Still ending amount is going to be 1,000. Principal still 500. If we go ahead and put in the 1 plus 0.0675 divided by 12, that's the number of times it's compounded annually, to the 12, and then again, we're going to be solving for the T. Again, my first step is going to be to divide by the 500, so I have a 2 equals, I've already calculated this, and it's a 1.006, we'll say, to the 12t. Now you have to switch this to a logarithm, so this is going to be a log base 1.006, but I will not use that rounded number. I'm going to use full values in my calculator of 2 equals 12t. All right, so in my calculator, I'm going to do that whole math, alpha math, to get the logarithm and be able to type in the base. But I'm going to go grab the 1.06 number to put it in as the base. and then put in the 2. And then I'm going to take that answer and divide it by 12. And I end up with t equaling 10 point, that would round to 30 years. All right, so takes a little bit longer, but hardly anything, right? Probably not dealing with big enough numbers here for this to make a huge difference going monthly versus compounding continuously. All right, so rather than me reading all of these to you, I'm just going to give you a minute to go ahead and read this number 2. Right, so I said earlier that you're probably going to be using that given model that I gave you at the beginning, and that's that y equals your initial value times e to the kt. So let's start filling in what we can. First of all, the initial value is going to be the 6 billion people that happened in 1999. So we're calling that kind of the initial year. And so I'm going to put in the initial is 6 billion. Now, what I might do is just write the 6 and just always know everything's going to be in billions. So keep that in mind as we go. So everything's going to be in billions. Now, the other thing, though, is I don't really know what K is for the world population. And so what I'm going to do is I'm going to use this other information sort of as an extra ordered pair that I can fill in to go solve for K. So this is ultimately an ordered pair, 2018, 7.504 billion. But it's not really 2018. It's how many years after 1999 would 2018 be? Well, that's really just 19 years later. So really this is an ordered pair of 19 and then the 7.05. Again, we're dealing with everything in billions. So that's going to be my X and Y. And then in this case, X is actually a T. So I'm going to leave my 6 there. I'm going to leave E. Remember, E is just a number. Suddenly went to red here. Let's make that red. And E to the, I don't know what K is, but the X, the time is 19 years. And the Y that goes with that is a 7.504. And now we're solving this. So in our calculator, we'll go ahead and do the 7.504. And we're going to divide it by the 6 to begin with. And so then we get a 1.25 equals e to the 19k. And now you're ready to switch forms. And so that's a natural log of, and I would go grab the full value on this, 1.25 equals your exponent. So in my calculator, I'm hitting natural log, go grab that number and close that parenthesis and divide by 19. So in this case, K is 0.0, I'm going to go 0.012. So all we're doing right now is developing the model. So the model, we're going to go back to the original, but it's a y equals, I'm going to stick with 6 being the initial, e to the, and I now know that K is 0.012 t. So here's the model that we have. Now, based on the model, what should the world population be this year? Okay, so depends on when you're watching this video, I guess. I'm going to say it is 2024 for this particular scenario. So 2024 would actually be 25 years after 1999. So in 2024, that's the equivalent of letting t equal 25. So I'm going to use my model and determine what the population should be. So I got y equals 6 e to the 0.012 times 25. And because I have it just sitting here in my calculator, I will go ahead and grab that full value on that 0.012 number. So in my calculator, 6 e to the, go grab that number, and then do a times 25 on that. And I end up at a y equals 8.053. And of course, that would be in billions. And just for the fun of it, I'm going to Google it. Now, here's the problem is I'm at the end of this. So I'm not real sure, like, are they doing it? Yeah, see, they're saying by the middle of 2018. So maybe we're talking about the middle of it. Okay, well, let's see. You can always get, if you get on, if you just Google it, you get a clock. It's just a running clock. And by Googling it, I got a 8.2 billion people. So maybe because it's later in the year, it's November. So pretty close. All right, if this trend continues, when will the world population reach 10 billion? Okay, now you're doing a problem a different direction because now you know the y. I'm going to come up here where I have a little bit more space to work. So I have a 10 billion equals 6 e to the 0.012 t. Solving for t here. So 10 divided by 6 is going to get you your 1.66. So I'll go 1.67. And then we're going to have to switch this again to a natural log of the 1.67 number equals your exponent. All right, I'm going to try to do full values on everything here. So I'm going to do natural log and go grab that number. And then I'm going to divide by and go grab the 0.012 number. And I end up with t equaling 43.39. And it says approximately when, so that's going to be 43 years after 1999. So I'm going to go with 2042 is the year that would happen. All right, so not as much going on this problem. Let's see what we've got. Suppose 600 grams of a radioactive substance are present initially, and 3 years later, only 300 grams remaining. Well, that right there is just a half-life. Because we have half of it left. So they don't talk about a half-life, but this really is a half-life problem. So to determine an exponential function that models this decay. So I'm back to my normal model, and I'll go ahead and write it here just to refresh your memory. E to the kt. All right, so let's see what we know. The 600 grams is going to be your initial, so I can put that in. And then they've ultimately given me another ordered pair. So I can go figure out what K is for this substance. And once I know the K, then I can write out the model. So the ordered pair would be 3 would be your time. 300 is your Y value, how much of it is. So here's 300. E to the K times 3. First thing you're going to do is divide by the 600, and you get a 1/2 right here. If you're trying to double something, you end up with a 2 there. I'm doing a half-life. It's going to be a 1/2. E to the 3K, and then you switch to a natural log. And then you just go straight to your calculator. You do natural log. I'll put in parentheses 1 divided by 3, and then divide it by the 3. And so my K value here is negative 0.0, or not, I'm sorry, negative 0.366. Now notice it's negative, which is indicating that it is a decay model. So here's the model. Y equals, the initial was 600, e to the negative 0.366 t. That's the model that we will use, the full value on that exponent. So how much will be present after 6 years? Okay, this is a little bit easier than those previous ones because they're giving me the t. So I just get to type this just straight into my calculator by putting a 6 right here. So 600 e to the, I'll go grab that number, take it times 6, and I get the amount of the substance would be 66.67 grams. All right, so let's try another one of these. Again, the longer one, so I'm going to give you a minute to read it. All right, so they're already giving us the model that we need. They want us to find the half-life of carbon-14. Now, my hint here is just make up numbers. You could start off with 10, and then it ends up at 5. That'd be half. I could start with 100 and end up at 50. But do you remember the very first thing you're going to do is divide by that number? And since it's going to be a half-life, it's going to end up a 1/2 equals E to the negative 0.0001216 t. And I want to solve this for t. I want to figure out what that half-life time, what that time was for it to do that. So oh, darn it. What was I thinking there? It's natural log of, did you catch that? You were like, what's she doing? Natural log of 1/2 equals your exponent, right? Equals your exponent. All right, so all I'm doing is typing in my calculator, natural log of 0.5, and dividing it by that big long number. All right, and so T is equal to 5,700 we'll say 0.22. That's in years. So what they're saying here is that the half-life is 5,700 years. It's going to take 5,700 years for that carbon-14 to decay half of what was existing. Okay, so then let's look at this next problem. Charcoal from an ancient fire pit on Java contained 1/4 the carbon-14 of a living sample of the same size. Estimate the age of the charcoal. Okay, so here my hint is to consider how long it will take to only have 1/4 left. All right, so if our half-life is 5,700 years, it's going to take that long for half of it to disappear. And then half of a half is 1/4. So ultimately, this is going through 2 half-lives. So if it went through 2 half-lives, that'd be the 5,700 twice. So I guess if I'm also including the 0.22, I would have, they're asking how old would it be? Well, it would be 11,400, and I would go 0.44 years old. This is just trying to catch that the 1/4 would be 2 half-lives. When you get through 2 half-lives, you're now down to 1/4 of it. All right, so I'm just trying to go through several different examples of where you can use these exponentials, and we like that just basic model to use a lot of the time, or sometimes there's going to be a special formula given to you. This is one of those special formulas. This is our last one. This is a formula that you don't have to have memorized, but you have to know it well enough that you can use it on the test. You have to know what all the variables stand for. So this is Newton's law of cooling. And they're saying that the rate at which a body cools is proportional to the difference in temperature between the body and the environment around it. So here's what I've got. This is the temperature at time t. This is the temperature of the surrounding medium. So that's when it said, and the environment around it. Okay, that's the surrounding medium. room temperature or whatever's going on. And this is your initial temperature minus your surrounding medium. You can see that it's going to be decay. The temperature there is going to be a decay because it's a negative K, but we don't know what K is. And K varies depending on what the thing is that is cooling. So in this example, it's coffee. It's going to be a coffee cup. And so we don't know what K is for coffee. So our first job, just like with previously, we have to go find the K. They give us information that we know everything except the K. We'll solve for K to create a real model, and then we'll be able to answer questions. Now, on this one, we have a coffee pot with a temperature of 100 degrees is set down in a room with a temperature of 20 degrees, and this is all in Celsius. Now, what they have ultimately given us right there is this is T sub O. That's your initial temperature right there. This is the surrounding medium right here. Now they give us a scenario that's going to help us fill in other numbers. It says the coffee cools to 60 degrees after 1 hour. Okay, so that's ultimately another ordered pair that we're going to be able to fill in. So here we go. We're going to use this formula. This, we know the TO, the TM. We know the time that it took to get to a particular temperature. So that's your X and your Y, or your extra information right here. So the ending temperature was 60 degrees. The surrounding medium was 20. Don't forget this plus sign. Lots of people ignore the plus and then they all of a sudden they're multiplying there. Be careful with that. 100 minus 20. E, don't know what K is for this coffee, but I know that it took 1 hour for it to get to that 60 degrees. So first step, subtract the 20. I'm going to go ahead and combine what's in the parentheses. That's going to be an 80 e to the negative k. Next, I'm going to divide by 80. Turns into a 1/2 scenario here. E to the negative k. Switch to a natural log of 1/2 is equal to negative k. And so on my calculator, I'm getting this to equal a negative 0.693, but that equals a negative k. So what I have figured out that k is equal to negative, sorry, not negative, k itself is equal to 0.693. So then the model, I'm actually going to write on the next page because the next page in your notes has some questions about this. So I'm going to write the model on our next page. All right, so this model, what I have filled in, this is your surrounding medium. That's not changing. This was the original. That doesn't change. This was my K value that I found. And so now what I have is a time with an ending temperature that I can use, I can find for any particular time frame for that cup of coffee. So it says find the temperature after a half of an hour. Okay, so I'm looking for the temperature. So that's going to be me solving for the T of T. I'll go ahead and call that an 80 e to the negative. I put the negative back in because the formula has the negative. It's a negative k, and I found k to be a positive, but then when I put it in here, it goes back to negative. And I know that my time, since everything was in hours, is a 0.5 or a 1/2. Now, you know everything on the right side, so really you're just typing in your calculator. Be careful with your order of operations. I'm just going to type it in left to right. I am going to go grab the full value on this. And the temperature that I got is a 76.57 degrees Celsius. Now, The other question, so that one, they gave you the time and looking for the temperature. The other scenario is going the other way. How long will it take for the coffee to cool to 50 degrees? So now I know the 50 degrees, and I'm going to go solve for the time. All right, first thing you got to do is subtract the 20. So that's going to be 30 equals 80e to the negative 0.693 t. I missed my t up there. All right, divide by the 80. And then you're going to switch that to a natural log of 0.375 is equal to your exponent. Just let the calculator do the work for you. I'm grabbing full values. I got my time to be 1.42. So how long will it take the coffee to cool to that? That's 1.42 hours. All right. So again, you do need to be able to work through the Newton's law of cooling. We always, I say always, pretty much always have to do it twice. You do it once to figure out what K is. You do it a second time to solve your problem. All right. Hope this helped. Good luck.